So yeah, my name is Balázs, and well, that name may look a bit strange, but I assure you that in Hungarian it's a completely normal first name. It's not very common, but quite a few people have it. And my last name Kish, well, I understand that in English it means something a bit different, though it's a very nice word. In Hungarian it just means small. So well, who am I? Who am I, and what is Sidereal, and what is this entire secure coding thing all about? So in my personal history, I have been working in the area of software security for about 13 years now. First as a security evaluator, which basically means that various software and hardware companies were giving us their products that we evaluated to look for weaknesses and vulnerabilities. And eventually, based on our experiences from this, we decided to move into a more proactive arena that is teaching these same companies and, well, anyone who would listen about what kind of mistakes to avoid while you are building your systems. Because obviously we saw the developers making the same mistakes over and over again. And yep, that is basically who we are at Sidereal. I will perhaps have a few minutes to talk about our training courses at the end. But that's essentially our origin story. And yeah, I've also been involved in several international European Union research projects in the topic of software security. I think this is a very important area, probably one of the most important, even within even within the general domain of cybersecurity. The security of software in particular is a very serious topic, and it's going to become more and more serious as time goes on. So in order to make sure that everyone will be able to focus on the material and not my perhaps less than beautiful face, I'm going to turn off my webcam shortly as we progress with the actual material. And as Pella has said, feel free to ask questions at any time. In the interest of keeping to the schedule, I'm going to be gathering all the questions and answering them at the end, so that we are not going to run over time, and we'll have a chance to answer all the questions together. So without further ado, let's talk a little bit about password policy myths. And before we get there, we will probably need to talk about some basics. So I mentioned before that my particular area where I work in is software security, and more specifically secure coding, which is a part in the software security arena. But what is software security? What do we mean when we talk about that? Software security is also sometimes called application security. And I am sure that we have all heard about all kinds of security incidents affecting everyone, from the smallest open source project to huge multinational corporations. If you just look in the news, you've probably seen a report of a Microsoft Exchange hack affecting hundreds of thousands of companies all over the world by exploiting several weaknesses in the software. And this has apparently been a very long ongoing attack. So all of these incidents that we see, from the smallest one to the biggest one, has one thing in common: the attackers exploiting some sort of weakness in the system. And most of these weaknesses are caused by programming bugs. And it's sort of an unfortunate fact of life when we are a programmer that we just never can be sure that we have got rid of every single bug in our system. Just like Murphy's Law say, that I'm sure some of you are familiar with, there's always going to be at least one bug somewhere in our system that we can find. So I can illustrate the problem with a simple diagram. Let's draw some circles here, or well, ovals. So this big oval here is going to be representing all of the bugs in our system, all of the bugs that we haven't found. Now, we don't know where these bugs are, and we, of course, if we can find them, we can probably fix them. But at this point, we don't even necessarily know that they exist. We may suspect them, but we won't actually know for sure. Now, a subset of these bugs, which is obviously going to be a much smaller circle, are going to be what we call vulnerabilities. And a vulnerability is basically a bug in the code which can be exploited in by an attacker, by a hacker or a bad guy, however you want to call them, in order to damage the security of the application. Unfortunately, we can't tell from the outside which bugs are vulnerabilities. because we don't even know about the bugs, perhaps. And so the only way to get rid of all the vulnerabilities is to systematically go through our entire program, our entire system, and try to fix every single bug, basically going it through it like this. And well, realistically, new bugs will keep appearing in the code as we add new features, which means that we'll have new vulnerabilities appearing as well. And of course, most of the bugs are not going to be useful to the attackers, but those that are can be exploited to potentially break the security of the entire system. And this is kind of a pretty big issue in general when we talk about application security, is how do we deal with this problem? Because we are starting from this situation that we cannot have 100% security. So things look kind of bleak when we look at it like that, but thankfully the situation is much better than it first appears, because about 90% of these vulnerabilities are caused by typical programming bugs that can be clearly identified in code. And since most of them have been around for some time, sometimes even decades, we have numerous protections and mitigation techniques available in various programming languages, application frameworks, secure libraries, operating systems, and sometimes even hardware. And even just taking care of these typical vulnerabilities will push you 90% of the way there. And well, the secure coding skills you pick up along the way can allow you to more easily find and fix the remaining 10%. And furthermore, making use of these widely available protection measures will help a lot in mitigating the consequences of successful attacks and generally making the job of the attackers much harder. Because for the most part, the bad guys are also rational actors. They also have finite resources, and if you make it hard enough for them to exploit a vulnerability, such as by getting rid of these typical mistakes, then they will look for easier targets instead. So Bruce Schneier is a well-known cryptographer and security expert, and he has a famous quote in this area that when you are trying to secure a software system, the goal is not 100% perfect security, but rather adequate security at a reasonable cost. If you look at it like a game theory question, this is called an infinite game, where you have two players, the developers and the hackers. And the goal is not to beat the hackers, because if they are motivated enough and have enough resources and infinite time, they will probably win. But rather, the goal is to stay in the game, especially compared to your competitors. So last month, in our previous webinar, we talked about outbound password management, which is managing passwords and other secrets used by our systems in order to authenticate to other systems. But today, we'll talk about the other side, inbound password management, or managing user passwords that are used to authenticate to our system. And well, passwords are perhaps the most often discussed cybersecurity topic, especially because this topic is discussed outside the cybersecurity arena a lot. As developers, we use passwords more than anything else when implementing authentication systems for humans. A lot of burden is put on non-technical end users to handle their passwords, which inevitably is going to cause some friction and conflict between end users and IT. Some security experts are pushing for a passwordless future when we are going to be relying more on biometrics like fingerprints and single sign-on systems, but that approach has its own challenges and it's definitely not going to happen over time. So the fact of the matter is that passwords are here to stay, and managing passwords is an unavoidable part of modern life, not even just like for a programming perspective, but for an everyday life, whenever you're interacting with websites, whenever you're interacting with any kind of internet-based service. An important part of password management is defining a so-called password policy, which is a set of rules that controls which user passwords are acceptable. And unfortunately, there are quite a few misconceptions floating around in this space, and many of them are accepted as good practices, even though they are not. So let's take a closer look and see why some common practices can actually make the situation worse. So let's start with the first password policy myth, which is relying on composition rules for security. So what is a composition rule? I'm sure we have all encountered a situation where we had to register to a service and faced a lot of demands about what characters to use in a password. Uppercase and lowercase characters, digits, special characters. These are all common examples here. But these kinds of requirements that the site or the application is putting towards us is what we call a password composition rule. At first glance, this looks like a good thing, because after all, when by requiring all of these special character types in our password, we are guaranteeing that the strength of the password will be higher, because we are increasing the number of possible characters that the attacker has to include in a so-called brute force attack. We'll talk about brute forcing later, but for now, let's just say that is the process where the attacker is trying every possible character for every single character in our password. It's much easier to brute force a password if we only use the 26 characters from the English alphabet compared to a password that's full of numbers, uppercase characters, and symbols. So this is kind of common sense. In theory, composition rules will thus significantly improve the entropy of our passwords. So what's the problem? The problem is the in theory part. Because if we force these composition rules on our end users, they won't suddenly start generating strong passwords on their own. Instead, these rules are going to be an annoyance to them, and they will be forced to find workarounds just to get the system to accept the password. If you go through the examples that we have seen here of requiring all these different types of characters, if we require an uppercase character, then the user will just capitalize the first character in the password. If we require a number, then they will just add the 1 to the end of the password. And if you require a special character, they will just add an exclamation point to the end of the password. And that's how we end up with password1 exclamation point. And these are all trivial transformations from the same starting point, which is the string password. And any attacker can thus add these types of transform passwords into the dictionaries that they're already using to break passwords. In the end, composition rules only made the users go through some extra steps, but didn't actually increase password strength. Now, composition rules are also problematic from another perspective, which is that they may reject a strong password just because it doesn't conform to our rules. If a user wants to use a random 20-character alphanumeric string, a password policy that restricts the passwords with composition rules, like requiring symbols or numbers in it, symbols or special characters in it, will reject it because it doesn't have those characters. Especially because for some reason, some of these policies like to put an upper limit on password strength, which definitely is going to make the passwords weaker in the long run. So let's take a look at a few examples. What you see on this slide are all from a public GitHub repository called dumb password rules, which specializes in documenting bad password policies through screenshots. And as you can see, there's a huge number of them. If you go and visit the repository, you will see that there are literally hundreds of examples. But we have picked a few of them just basically at random to illustrate this problem. And well, what can I say? The internet truly has everything nowadays. So we can see through these examples that all of them are putting some type of restriction on the end user, which will ultimately make the password weaker. For example, in the first example that we see here is going to restrict the first character of the password to a relatively narrow list. Like you can see, the first character has to be one of the following. It has to be an alphabetic character or a $sign or a hash. And this is going to restrict the types of passwords that the user can come up with, which will then indirectly weaken the password. We can also see similar problems in the other examples that there's going to be some requirements for including special characters. Then you also can have a requirement here, for example, that in the last example, you cannot have certain types of characters in your password, which is also a bit strange. So there is something else that these examples have in common, which is that they all have an upper limit on password length. We can see that the first one restricts passwords to be between 8 and 9 characters. The second one puts an upper limit at 20, which is actually not too bad, but as we'll see later on, it does restrict some types of password from being successfully used. And the last one has a limit of 8 characters. So this restriction will severely limit the strength of these passwords when it comes to brute force attacks. Nowadays, an 8-character password is within a reasonable brute force range for a motivated attacker, especially if the developer doesn't use the right algorithm to store the password. In summary, password composition rules are much more hindrance than help in practice, and they are frequently accompanied by rules that actually make passwords weaker in the end. So let's take a look at password policy myth number 2, which is password expiration. This is another very common sentiment, which is regular expiration of user passwords. The idea behind this is to protect the password against potential brute force attacks by limiting their lifetime, as well as limiting the impact of potential breaches that reveal the password. And limiting the lifetime of a secret is generally a reasonable sentiment when it comes to cryptographic keys, and it's part of the reason why digital certificates, for example, have an expiration date. And applying this requirement to administrator passwords and API keys makes sense because those should be long randomly generated strings that are rotated regularly anyway. But it doesn't translate well to end user passwords in particular. The first problem is that compared to the resources needed to brute force something like a secret key, which is ideally going to be at least 128 bits of random information, brute forcing a password is actually really, really quick. And of course, in this context, I am referring to offline attacks against the password database, which stores the hashed or otherwise transformed versions of the passwords. And in that case, the attacker is able to find out the password by hashing every possible combination of characters and comparing the result to the hash stored in the database. Modern hardware can generate hundreds of billions of hashes per second for weaker algorithms. And for stronger algorithms, such as PBKDF2, scrypt, bcrypt, or Argon2, it is still feasible to find out weak passwords by a dictionary attack if we are relying on users using weak passwords. Next, if we require our users to regularly change passwords, in practice, they won't come up with a strong password every time, especially if this is something that they just have to do when they log in one day and they suddenly get a message that says, you must change your password right now, otherwise you can't log in. It's much more likely that when something like this happens, that they will just reuse an earlier password with a minor variation, which doesn't actually make the job of the attacker significantly harder, because it's very likely that the password brute forcing process will be incorporating such minor changes into the dictionary as well. So in the previous example, we go from password 1 to password 2. So that's not going to be a significant increase in security. And another problem is that if we require very frequent password changes, our users will just take the path of least resistance, which may be literally writing down the passwords physically on a post-it note, which can, of course, enable other types of attack, how a particular attacker who has, let's say, access to the thrown out garbage may be able to find these pieces of paper and find out the passwords like that. And this attack is called dumpster diving. But basically, it's going to expose the password. That's the problem. But there is, of course, a counterpoint to be made here. What about breaches? After all, if you suffer a data breach and the password database is leaked, then everyone needs to change their password. There's no question about that, because obviously the passwords at that point have been compromised. But the challenge is when a breach happens somewhere else. So not at your particular service or your particular website, but some other website where the user is using the same password both on your service and the site that has been hacked. What can we do? And the answer is, this is not really something that we particularly can do anything about, because we are not storing the password of the user. We don't know the password of the user. We are only storing a version which is a salted hash, basically a one-way transformation of the password. So we don't actually know the password. And there is no way for us to tell if any of our users have used the passwords elsewhere. And also, these kinds of breaches of major internet services happen all the time, sometimes multiple of them in a single day. There are several websites that document this. It's a very well-known one is haveibeenpwned.com. So in summary, don't force users to change passwords periodically, because in the end, it will just make their passwords weaker. So let's take a look at password policy myth number 3, which is password hints. So humans, well, we are made of inferior flesh compared to metal, and we have the disadvantage of being forgetful. It's reasonable to assume that users will forget their password at some point. And the password hint is a feature that helps the user experience, because when the user registers, they can set a reminder text for themselves. And when they log in and they don't know their password, then they can get this reminder text, which will help jog their memory and figure out what the password is. At first glance, this looks like a good idea because it encourages users to have stronger passwords because they can have some assistance which helps them remember in case they forget. And another related feature is password suggestion, which in this case means that you are basically telling the user to think of a certain type of password instead of just telling them to think of whatever password they can think about. Because instead of just generating a password without guidance, you can give the user a prompt saying, what street did you grow up on, or what's the name of your favorite pet. And in this case, you are giving the user a suggestion about what kind of password to create, which of course, again, helps remember what the password was in that particular site, because you can just ask this question when the user logs in, especially for password recovery. This is a technique that's very commonly used. So, well, what's the problem with these? In short, these make the job of the attacker a lot easier. Consider that these password hints are also displayed to the attacker. So if the attacker knows the username of the victim, they can just log in, fail, and then they will get the password hint. In many cases, the password hint will contain public information that is trivially easy to guess or find out with some minimal research. An example is this name birth year combination that we can see above. And this was something that was revealed in the Adobe breach in 2013. A particular user had the suggestion, or should I say password hint of name birth year, and their password was Mike 1953. Everyone with some minimal investigation could find out that this person's name was Michael and that they were born in 1953. This is information that's usually displayed on Facebook and other kinds of social media sites. And from that point, it was trivial to find out the password. And the password suggestion has a similar problem because in addition to being easy to guess, many of them are restricted to a smaller list, such as last names, first names, or street names. And these are all going to be relatively easy to break with a dictionary attack. It's much easier to go through 100 possibilities compared to 100,000, basically, especially if you are doing an online attack against a service instead of an offline attack. So what these two things have in common is that they add a weak link to the system, and the attackers are always going to go for the weakest link. If it's easier to break a password based on a password hint, they are definitely going to do that. So in short, don't use password hints and password suggestions. In fact, it's a good idea to try to avoid security questions entirely as a primary method of authentication. Now, for the last myth, myth number 4, let's take a bit of a different track, because we have seen some bad examples about what happens when we limit the users in what passwords they can create. So it stands to reason that we should not have any limitations at all, because trying to enforce a minimum password strength is just going to backfire on us anyway. So this assumption is not entirely incorrect, but it is still dangerous, because it's true that restricting what kind of password the user can pick is going to limit password strength. But is it really okay to just allow them to pick whatever password they want? And the answer is, well, no, because users will try to gravitate towards the path of least resistance, and they will choose very weak passwords if they can get away with it. And many of these passwords can then be trivially broken with a dictionary or by a few simple guesses, like just trying to guess the username or some other public information that's available trivially for that particular user. So we may think that just setting a minimum password length will solve this problem, because after all, long passwords are significantly harder to break. This is true. In fact, the biggest determinant of password strength is password length. But if you don't have any rules at all, a user can pick a trivial password, like just the 0 character repeated 20 times for a password, and that is definitely going to be in a dictionary that the attacker is going to use to try and gain access and break the user's password. So in short, we should not set composition requirements towards password, but we still need to have some sorts of restrictions in place. And we definitely need the way to forbid users from using trivial passwords in some way. Thankfully, this is something that we can do with in using several different techniques, and there are some tools that help us with this as well, and identify easily breakable passwords so we can reject them. And we are going to be talking about that. I'm going to be talking about that in one of the later slides. But one example of a tool like this is ZXCVBN. And as you can guess from the name, because it's basically the bottom line of the keyboard, it's good at identifying passwords that are easy to guess because they are representing a trivial pattern that is probably going to be in any kind of password breaking dictionary. So, okay, now we have seen what a lot of developers are doing wrong, but how can we do it right? Let's dig a little deeper and see why a good password policy is important and how you can implement it. And also, more importantly, see that this is not just us random security people saying this, but this is actually an industry standard requirement. So there is a core problem which makes password-based authentication difficult to secure, the strength of the passwords themselves, because, well, us humans are not very good at coming up with strings that are easy to remember but hard to guess, which is what a password should be. But machines are very, very good at breaking any of the predictable passwords that users come up with. So we need some sort of way to ensure a baseline level of security for passwords. This is done through a so-called password policy that specifies minimum requirements towards all passwords. The ultimate goal of a password policy is ensuring the password to be random enough so an attacker cannot easily guess it, and making sure that none of the passwords that we use are in common password dictionaries to prevent dictionary attacks. If we have a good password policy, the attacker will need to perform brute force attacks to learn the passwords, and that is significantly more expensive than a dictionary-based attack. To accomplish this, whenever a user sets their password, it needs to comply with the password policy. And if it does not, the password must be rejected and the user must be told why the password was not acceptable. But when defining a password policy, it's also very important to ensure a good user experience. This is also known as a secure design principle of psychological acceptability. What this means is that basically, if a password policy is unreasonably difficult and to comply with, or the authentication process itself is very annoying to use, then users will find a way to bypass it entirely. Unfortunately, this conflict between security and usability comes up a lot, and it's the job of the developer to find a good balance that provides a good level of security without pissing the users off. This is illustrated by this photo on the right. In this case, somebody tried to control the flow of cars going through that road with a controllable barrier. But it annoyed the drivers enough that they decided to just drive around the barrier completely. Even if they had the necessary key card to open the barrier, it was easier to just go around it. And this is kind of a callback to myth number 1 and number 2. If you make your password policy too much of a pain for end users, they will either just stop using your service or they will find ways to work around your annoying policy. So let's take a look at what kind of standards exist for password policies. In particular, let's see what the National Institute of Standards and Technology has to say about password policies. This is a summary of Special Publication 863b from 2017, which deals with all kinds of topics related to authentication. First of all, length is an extremely important aspect of password security. 8 characters are an absolute minimum for regular passwords, so you must not have a password that's shorter than 8 characters. There is an allowance for temporary passwords to be 6 digits long, because after all, those are supposed to be temporary and not persistent. And more importantly, whatever user interface element accepts a password, it must be able to accept at least 64-character passwords and must not truncate passwords in any way. Think back to some of the examples from myth number 1, where we had policies that restricted passwords to be 9 characters long at most. It also says that Unicode passwords should be supported as well. So if someone wants to use a bunch of emojis for a password, technically you should be able to support it. Of course, this is mentioned as a should in the standard and not a must. So you don't need to do this, but it does make the password space much bigger if you can support Unicode characters. And well, let's move on to the next topic here, password hints. So remember password hints from myth number 3. They are a mechanism that can be used to help someone authenticate even if they can't remember their password. Like, for example, your password is your year of birth plus the name of your favorite sports team. Password hints are a huge help to attackers, and for that reason, they must never be used. And the same thing applies to secondary knowledge-based authentication, which is used to bypass authentication, such as answering a secret question like the name of your first pet, because these are much easier to break than a password and thus will degrade the strength of the authentication control. Deciding whether a password is acceptable or not should be based on a blacklist. So just a short definition here, a blacklist is a list of known bad inputs that the system won't accept. On the other hand, a whitelist contains a list of known good inputs where the system rejects any input that's not on the whitelist. In software security, we generally prefer whitelists when validating inputs because with a blacklist, you always have the risk of not including all the possible bad inputs. But the password policy is one of the few areas where a blacklist is preferable to whitelist, and it intuitively makes sense because after all, we can't and shouldn't define all possible passwords a system can accept. There's not enough space that we have on our hard disk to do that, but we should define passwords that should not be accepted. And such a blacklist should contain common dictionary words, repetitive characters, and context-specific words such as usernames. And this connects nicely to myth number 4, giving some guidance on what kinds of passwords should never be accepted. However, as a very important difference from common practice, there should not be any rules for password composition. So this is explicitly mentioned in this standard, which means that rules like password must contain lowercase, uppercase, and special characters, because as NIST has found out based on its own studies, this has been proven to actually make passwords weaker in the long run. This is what we talked about in myth number 1. And if a password is not acceptable for any reason, then the user should know why the password was rejected. Another important point that goes against common practice is that there should be no periodic expiration. This is also mentioned in the standard here. Just as with password composition rules, it's been proven that forcing users to periodically change their passwords will only result in weaker passwords overall in the long run. As mentioned in myth number 2, the only acceptable scenario for a forced password change is when you have a security breach where all users have to change their passwords anyway. And from a cryptographic perspective, they have some requirements about the sizes of the salts, which are the random strings that you generate when you are storing a password at least 32 bits, and also that there should be a so-called system-specific secret salt called the pepper, which is another, which should be a secret value that is generated by the server when in advance, and it's used, but it's concatenated with the password before generating the hash and storing it in the database. The difference between the salt and the pepper is that the salt is a value that can just be stored in the database in plain text, and the pepper is and the salt is unique for every user, but the pepper is a constant value, so there's only one of it, and it's included in every hash operation, just like the salt, so it's included next to the salt, but it's not stored in the database, it's stored in some sort of protected location, so that even if the database is leaked, if this secret information is not revealed, the attackers cannot break the password database. And finally, to help with user friendliness and psychological acceptability, password-based authentication should support pasting passwords. This is required because a lot of users have password managers which need copy-paste functionality to transparently send passwords to your user interface. And they also need a way to display the password temporarily for the user while they are typing, because especially on mobile devices, it can be difficult to type long passwords. So as we have seen with the NIST standard, passwords should be accepted or rejected based on a set of rules. Let's take a look at some of the most commonly used rules, and by using them, you can ensure that all of the user passwords are sufficiently hardened against guessing and simple dictionary attacks. The main challenge is, how can we assess the strength of a password? This is one of the few situations where a blacklist is useful because we only want to forbid a limited number of known bad passwords as well as any passwords that match the patterns listed in the NIST documents. We also want to prevent users from just using public information in their passwords that the attacker can trivially obtain. First of all, the password must not include either the username nor any information that's in the user's public profile if you have a public profile anywhere in your application. This includes information like city of residence and date of birth. There should also be some rules in place to prevent trivially easy passwords. And bad passwords include any word from a dictionary or a password dictionary, passwords containing repeating patterns, trivial sequences like 1, 2, 3, and keyboard patterns like QWERTY. There are tools used to validate passwords against these rules. A commonly used one is the one I mentioned before, ZXCVBN. It's open source. It's available in GitHub in several different programming languages, and that is one of the tools you can use to basically filter for these kinds of bad passwords. But of course, this still all comes with a caveat, because even if you have all of these rules, there is still no guarantee in the end that you can have a guaranteed strong password for your end users. Because there are always going to be edge cases for someone coming up with a password which satisfies all aspects of your password policy, but may still be weak because it may be close enough to a dictionary word that an attacker may include it in their own dictionary anyway after doing the transformations in order to get to this password from the basic word. There also may be difficulties in measuring the password strength of non-English passwords. For example, this long string, JI, etc., looks strong, but if it's transliterated to Mandarin by using a Taiwanese keyboard, it will actually mean my password. So if you are just looking at it like a string, it will look strong, but this is actually one of the weakest passwords in the world. But nevertheless, using a tool to harden passwords is a good idea because it follows the defense in-depth philosophy of secure software development. So what is the right password then? What kind of password should we be using? Because to summarize, ensuring good password quality is difficult. For a long time, developers used this previous iteration of this publication, which was defined by a researcher called Bill Burr, and that is what defined these composition rules in the first place, like uppercase, lowercase, numeric, and special characters in 2003. And this is what led to myth number one. From a theoretical standpoint, these requirements were correct because if you're just looking at it like an ideal world, then these would be then requiring things like uppercase characters, lowercase characters, numbers, and special characters in a password will make users pick better passwords. But in practice, people actually chose weaker passwords because they just added a single character to fulfill the rule, and it was trivially easy to guess. For instance, if the password policy required a number, the user would just put a 1 at the end of the password. For this reason, the author of the original standards has publicly regretted this. There's an interesting interview in the Wall Street Journal in 2017 where he talks about how this particular misconception came to be. You can see that he even used these special characters in the title of the article to make fun of his own composition rules. But that brings us to perhaps the most important thing about password strength. Even considering all the various composition rules and password hardening techniques, there is a central truth. The strongest determinant for the strength of a password is just the length. As long as the password is not completely trivial, a password that's 10 characters long is going to be much, much harder to break than a 9-character password. For this reason, so-called passphrases are now considered to be the strongest and most useful password type. A passphrase is conceptually simple. The user just puts several dictionary words next to each other, and the composite word is what we call a passphrase. It's true that the entropy or unpredictability of the individual words is relatively low, but as long as the user chooses at least 4 or 5 words, meaning that the final passphrase is going to be around 20, 30 characters long or even longer, it's actually going to be much stronger than, let's say, a randomly generated 8-character string with some additional characters added to the end of it. And unlike this random string, the passphrase is going to be very, very easy to remember because it builds on dictionary words that the user already knows. This XKCD comic that some of you may have seen before on the right indicates this difference between a password that looks strong but is actually significantly weaker than a very simple looking passphrase. And well, in the end, the passphrase is the one that comes out ahead. Of course, the downside of passphrases is that because they are long, they can take a very long time to type, which means that from the end user perspective, it's also a good idea to use password managers. But that's a different topic. We are mostly talking about the perspective of the developer. So let's see why it's a bad idea to rely on security questions and password suggestions, as I talked about in myth number 3. In this demo, I'm going to try to gain access to a user's account by exploiting a weak password reset implementation. So what we are going to be looking at here is an example of an application that we are running inside our own virtual machine. And in this application, we have a very simplistic user password reset functionality. So if you look at the code here, we can see that basically how this works is that we require these 4 inputs from the username, the name of the first pet, the new password, and to confirm the password. So the problem here is that we are relying on something like the name of your first pet in order to reset the password, which can be much easier to break than the password itself. So let's take a look and see how easy it is to break. And once the main page loads, we can try to log in. Let's say that we don't know the password of the target user, so we are going to try to log in by resetting their password. But of course, we don't know the name of their first pet either. So we are going to be using a tool called Hydra, which is an online brute forcing tool that basically does repeated requests to this site. And using a password list, it will try every possibility and see when it succeeds or not. So just to briefly take a look at what we are going to be using here, this is going to be the password list that we have. It is really simple. It is something you can find on the internet. It's just a list of common cat and dog names, because we go with the assumption that most people have cats or dogs as their first pet. So if you just list all the cat and dog names in the world that are used, of course we are using an English perspective here, so English speaking world perspective, then it's very likely that we are going to be successful. And you can see that this dictionary is very small. It's only a little above 200 variations. So that means that even if there is like some strong protection of like only allowing 10 requests per minute or whatever, we can still break this password really easily. And that's basically what we are going to do here. We are going to make requests to this site. We are going to try to make a request to the reset password page by filling in the username as Charlie78. That's the account that we want to break. And for the password that we are breaking is actually the name of the pet, and we are going to be using this cat and dog names txt file for the source of that. And if we are successful, we are going to set the password to hacked. So we are setting both of the password fields to hacked. And yeah, this is going to run for a little bit. And the keyword is a little bit. It will not take longer than, let's say, 20 seconds or so. Even though it takes some time to make these requests, it will not take long at all to find the correct password, which in this case was Sally for this user. And after this, of course, we have successfully changed Charlie's password to hacked, and we can now log in. And basically, we have managed to exploit this password reset function that used the weak password suggestion to gain access to the victim's account. So, all right. And to wrap things up, and after this, we'll be going to the questions, let's talk a little bit about how can you learn more about these topics, about these software security questions where developers may be doing something wrong, whether on the design level or implementation level. And this is what we are trying to give in our courses. when first we talk about a particular issue, whether it's a design flaw or an actual bug. We talk about the problem, we talk about how serious it is and where it appears in the code. Then more importantly, we show how it can be exploited, like we have just seen here. We actually show some sort of practical example in a virtual machine environment where you can take a look at how that particular vulnerability is exploited. Then we try to speak about the best practices, what you can do to protect yourself against these kinds of problems. And if available, and usually there are real-world examples, try to present some real-world stories from famous hacks from the last few years. And unfortunately, there have been so many of these that we actually have a lot of case studies for a lot of different types of vulnerabilities. And yeah, this is all guided, as you may have seen in the demo. It's guided by a sort of chatbot-like plugin in a integrated development environment that the participants can use to kind of look at the problem, fix the code, and get hints about what to do, basically guiding them through these particular steps. And we have a lot of material covering several different topics in different programming languages like C, C++, Java, C#, and Python, as well as different areas like web, IoT, and application security in general, and also covering several industries, industry-specific questions like banking and finance, PCI DSS, automotive, healthcare, and machine learning.